All right, welcome back to section 3.5. We're going to be looking at the question of the day. Is the cardinality of the points inside the square S greater than the cardinality of the points of the line L? So first, let's make our predictions. If you didn't already, do it now. And now we're going to re-examine these figures. And I'm just going to divide it up. And I'm going to say, okay, the line segment is 0, 1. See how it's got that same length as one side of the square. And I'm just going to go as if it was on a coordinate plane. Okay? So I'm saying that this is the x-axis and this is the y-axis. And that if we go x across and y up, we get a point xy. All right? And that's just so we can kind of grab those points. So maybe first here, consider this. First of all, let's notice that the base of the square is exactly the same length as L. If we drew any horizontal line across the square, we would have another line that is exactly equal to L. So we would have lots and lots and lots of copies of L inside the square S. In fact, if we were to imagine kind of inking up the line L and then dragging it up the paper exactly 1 unit, we would make a square ink blot exactly the same shape as S. So if we have a different copy of L in the square of S for every single point on the vertical edge of S. So the cardinality of L is not bigger. We know that. We know that it can't be bigger than S. So either the cardinality of L is less than or equal to S. And so when we look at this, we might think, well, S must be much bigger than L because it's a whole extra dimension up. And it allows us to stack and store infinitely many L's in the vertical direction. So it's reasonable to conjecture that the cardinality of S is greater. But so far, all the examples we've looked at have had the same cardinality, so perhaps that's the trick here too. And I'm going to tell you that the cardinality of the square is actually not greater than the cardinality of the line segment. So pause here and just kind of think about that, and then we're going to look at this in terms of those barrels. So to show that the cardinality of the square is the same as the cardinality of the line segment, we're going to show that we compare each point of S with a point of L and each point of L with a point of S. So in other words, suppose we have those barrels, and in one we have all the points inside the square. Every point inside the square S. And in the other barrel, we have all the points on the line segment L. And if we could demonstrate a way of pairing elements of S with the elements of L, and we can show that once all the pairings are made, we have nothing left in the barrel, that would demonstrate that the cardinality of the things in the S barrel is the same as the cardinality of the things in the L barrel. Now, it's going to get a little tricky, and we're actually going to do something wrong before we do something right. So first, we're going to want to be able to precisely name those points in S and L. So recall that every real number can be expressed with an infinitely long decimal expansion. But remember that we also proved that 1 is equal to 0.99999. So we're actually going to, instead of kind of those rounding, we want to make sure everything is really precise. So instead of saying 6.5, anytime that we've got those 0, 0, 0s, we're going to think about it in terms of the 9s. And remember, these are equivalent. We already proved that. But we're just going to do that so that we don't have multiple numbers in there. Okay. If we take a point in the square xy, remember this point here, xy, we can write both x and y as infinite decimals, as you can see here. So to figure out which point on the line L we're going to pair with xy, we're going to just do something really weird, which is we're going to shuffle the digits of the decimal expansions of x and y together. Think of it like a deck of cards to create a new decimal number. So we create a new decimal number by taking 0 and then tacking on the first digit in x. So the first digit in x is 9. And then the first digit in y is 4. Then tacking on the next digit of x, which is 9. And then the next digit of y, which was 4. And then the next digit of x, which was 7, and 4. And we keep repeating that until we get an infinitely long decimal expansion. Then that new number is between 0 and 1. And it's a number L on L. This number here, z, is a point on L because it's between 0 and 1. And that we're going to associate with the point xy in the square. All right, so these would be the two numbers we pulled out of the barrel. This is the point on the square we pull out of the barrel, and this is the point on the line that we pull out of the barrel. So two different points in the square get paired with two different points on the line. And this correspondence keeps going in such a way that no two points of S are paired with points of L. And even though this seems really clever, there is something a little bit wrong with this, and we need to make sure we clear it up before we go back. So surprisingly, some points of L were not hit in our shuffling correspondence. And that is some points of L were never paired with S. And the reason why has something to do with the numbers inside it, the way that we shuffled it. So let's unshuffle it first. So let's think of that point L given by the decimal, this guy here. So here is an L point. So we're going to unshuffle it to find its corresponding point on S. So the point on S would correspond to 0 point, and remember we take the first digit for X. So this would be a 3 for X, and then the next digit corresponds to the Y, so that would be 7 for Y. And then the next digit is an X, so that's the 9, and then the next digit is a Y, that's a 0. 9 goes to X, 0 goes to Y, and so on. But remember here that 0.700 is actually the same as 0.699999. So it's not a unique point. This point, remember that this is the X. This point XY is actually the same as this point XY because these two values are the same. So if we have a point S that goes to this point, 36999, it's the same as going to 3.7. And so it gets lost. So this point here, 3.79090, is left without a partner from the shuffling because of that duplication. So even though we will have nothing left in the S barrel, there will be numbers remaining in the L barrel. So we need to not panic, right? Often when we try something and it doesn't work, it doesn't mean we have to scrap it. We just have to think about it. What's getting us into trouble? And it's the alternating zeros. These alternating zeros are giving zeros to the Y and none to the X's. So to avoid this, let's just modify the shuffling. Instead of shuffling the numbers perfectly, 1 to X, 1 to Y, 1 to X, 1 to Y, let's shuffle groups of digits. And we'll put down a few digits of X, followed by a few digits of Y, and so on. So how should we group them? Well, we know that zeros are the issue. So let's group all consecutive runs of zeros together and include the first non-zero digit. If there are no zeros, then the non-zero digit from their own individual group. Let's see an example. Okay. So we've got our X here. So to get to our Z, we take the 9, and that goes there. And then we go to the 4, right? We haven't come into any zeros. We take the 5, we go to the 4, no zeros. We take the 7, we go to the 4, we take the 8, and now we go to the 4, and now we've got a 0. Instead of just taking the 0, we take the 0 until we get to the first non-zero digit. So that's 0, 8. Then we grab a 4, and a 6, and a 4, and a 4, and an 8. And again, we get to the 0, 3, and we're going to pull that. And you see how we got these 0, 0, zeros go to the 7, and so on. And that way, we're not going to have alternating zeros. 0 is always going to come with a non-zero number. So we can check that this new shuffling technique goes to 1-to-1. Because in this case, every element of the line is paired with one and only one element of the square. For example, in the previous problem, the point on the line 0.37, and this was on L, 0.379090, this point gets paired with the point on the square. The zeros don't travel alone. So we've got our XY. So the 3 is going to come to there. The 7 goes to there, the 9 goes there, and now we get our first set with a 0. So this goes 0, 9. And then this gets 0, 9. And then this gets 0, 9, and so on. And so we're not ending up with a 99999, which will round anymore. And so we can show that through this process, we will never have repeating or duplicates, and therefore it has the same cardinality, every point on XY, every point is going to correspond to an unshuffled, a shuffled up. We've got our unshuffles and our shuffle. They're all going to correspond, and we can show that they have the same cardinality. And that concludes section 3.5.